Assalamu alaikum. Good morning. Warm greetings and sincere thanks to everyone for your valuable time. I am truly grateful and honored to all of you for your presence here. First and foremost, I would like to express my heartfelt gratitude to our respected supervisor, Professor Dr. Abdul Khalik sir, and to our head of department, along with all our honorable faculty members, for their exceptional guidance and teaching excellency, which have greatly shaped and broadened our pathway towards our higher learning. Here I am Ivan Ahmed. I am excited to present the culmination of our research work for the Masters in Environment Management titled Optimizing Thermal Comfort in Architectural Design, a climatic response study in Dhaka, Bangladesh. Let's move forward with the presentation. In this presentation, I am sharing the background of my study, the problem statement, research objectives, methodology, key findings, and conclusion. Today, Dhaka stands as a dazzling metropolis. The towering glass-clad buildings of the Gulshan, Bonani, Dhanmondi, and Motizil and other areas, the city at times appears comparable to Kuala Lumpur, Singapore, Bangkok, or any other developed metropolis of the world. Most of these high-rise buildings are wrapped in glass facades which absorb and trap solar radiation, raising the internal temperature of the building. To counter this heat, the mechanical air cooling systems are extensively used, which in turn emit more heat into the urban environment. The vicious cycle contributes to the continuous rise in Dhaka's ambient temperature. Three major types of problems have been identified here: building performance problem, economic problem, and environmental problem. This diagram illustrates the different ways heat is transferred within a building. We can see the solar radiation directly affects the roof, walls, and windows, especially those with glass facades, allowing heat to penetrate inside. At the same time, heat is also conducted through building materials and accumulated within interior spaces. Mechanical cooling systems then work to offset this heat again, but they also contribute to future external heat emissions, particularly in dense urban areas like Dhaka. As a result, the overall thermal load increases both inside the building and in the surroundings environment. Our research objectives are identify thermal comfort challenges in Dhaka's urban buildings, evaluate passive design strategies and innovative technologies, develop climate responsive design guidelines. Here is the key characteristics of Dhaka's comfort zone. Temperature in hot and humid seasons, the comfort temperatures are 26 degrees Celsius to 32 degrees Celsius. In the cooler month, it is 20 degrees Celsius to 26 degrees Celsius. The humidity 40% to 70% is comfortable. Air movement 0.5 to 1.5 meter per second. During summertime, the wind direction March to April, the southeast wind dominates, and the May to June, south to southwest wind becomes stronger with the approach of monsoon. The average wind speed in this month 6 to 10 km per hour, but higher during storms and heavy rain. The residents of Dhaka are more tolerant of the higher temperature compared to global standards due to local customs and climate adaptation. Fenger's model explains thermal comfort as a balance between heat produced by the human body and heat lost to the surrounding environment. It considers six key factors: air temperature, humidity, air velocity, mean radiant temperature, metabolic rate, and clothing. From these two important indicators are calculated PMV or predicted mean vote, which measures how hot or cold people feel, and PPD or predicted percentage of dissatisfied, which estimates how many people will be uncomfortable. The adaptive thermal comfort model is particularly relevant for Dhaka. Here, many buildings depend on the natural ventilation. Biophilic design principles are the most significant factors to optimizing the thermal comfort in the building. Our research approach is mixed method approach combining both qualitative and quantitative. It integrates field observation, climatic data analysis, simulation modeling, expert feedback. A destructive and analytical research design was adopted to understand the existing thermal performance of buildings. Data collection: we collected both primary data and secondary data. We use SketchUp as a simulation software, PMV and PPD as a comfort indices, and destructive and comparative method were applied to evaluate data consistency and results. Analytical framework identify existing thermal comfort issues in Dhaka suburban building, analyze climatic data and comfort users survey, model alternative design strategies, compare simulated result and occupant feedback, formulate climate responsive design guidelines. Results were validated through expert consultation. Simulation outcomes were compared with actual field data for reliability. The methodology helped develop an integrated framework combining passive design strategies and innovative technologies. Passive design strategies based on five key factors mainly, that is orientation, shading, ventilation, evaporative cooling, greenery. Building orientation plays a vital role in maintaining thermal comfort. In this context, the sun's path align with the prevailing wind direction during summer time. The diagram here illustrates the appropriate orientation of the building, which optimize both natural air flow and solar radiation for improved indoor comfort and energy efficiency. Shading plays a crucial role in maintaining thermal comfort. Throughout the year, the angle of solar radiation changes, striking the building facade at different inclinations. Therefore, the wall to window ratio becomes an important design factor in controlling heat gain. The Bangladesh National BNBC National Building Code also provides specific guidelines regarding shading and facade design to ensure better thermal performance. Various ventilation strategies play a significant role in improving thermal comfort, such as single ventilation, cross ventilation, stack ventilation, and hybrid ventilation systems. Among these, stack ventilation is the most effective natural method where warm air rises and escapes through upper openings, allowing cooler air to enter from the lower openings, thereby maintaining a comfortable indoor environment. Evaporative cooling lowers air temperature by using the natural process of water evaporation where heat from the air is absorbed to convert water into vapor. It is an energy efficient and eco friendly method suitable for warm and dry climates. Greenery helps improve thermal comfort by reducing heat through shading and evapotranspiration. Plants on roof, walls, and surrounding areas lower surface temperatures and enhance the overall microclimate sustainability. Our case study Karuponno Rangpur Limited, a factory building designed by Nakshabid architects under the leadership of architect Baizid Mahbub Khondokar. This project creates an eco friendly ecosystem. The design thoughtfully integrates passive design strategies, natural ventilation, daylighting, and locally sourced materials, which together enhance the thermal comfort and energy efficiency, resulting in a sustainable and climate responsive environment. So here we do first a comprehensive analysis identified the thermal comfort challenges. Second, the study thoroughly evaluated various passive design strategies and innovative technologies demonstrating their potential effectiveness in mitigating heat stress and reducing reliance on mechanical cooling. Finally, integrating the findings from these evaluations lead to the development of climate responsive design guidelines. Thank you.